small mistake I made. I was not careful enough here. When I defined in that very, in the most general case, Borel action and the space of orbits, I was careless, and the quotient sigma algebra on the space x mod g should have been taken to be the universal one. I describe it in two terms which are not necessarily equivalent. One should take the quotient sigma algebra to be the largest sigma algebra such that the map x to x mod g is measurable. In many cases, for example, if g is if x is a standard Borel space, and if g is locally compact second countable, it is the same as what I said. In a slightly more naive way, you push measurable sets, and you take a sigma algebra generated by all the images, but maybe the pre-image of something you pushed is not measurable a priori. So one should take care of this. I mean, I think in the way I described it, I was using this here, but you should observe that there is no need to use that description, that wrong description I gave when you observe this claim over there. I mean, this is true in any case. Just be careful when you do the exercise. Okay, so let me get back to the business. Good here. So I discussed. Soon I will move to another subject, which is Lebesgue spaces. What?
No, that's his chaotic way of signing you.
So it's not more criticism? So let me make some more observation. So soon I will be moving to discuss Lebesgue spaces, not only Borel spaces, but before I want to make some last observations about Taine Borel actions. So proper actions, proper topological actions are Taine. Clearly, I mean, you have a nice orbit structure. Orbits are closed, not only locally closed. In particular, any topological action, any continuous action of a compact group is Taine. I guess I already see that, again, I'm still slopey here when I say any or proper without the second countability adjective and without the T0 assumption, and this is not true, but take a nice T0 second countable space. If you have a proper action, then it is Taine. If you have an action of a compact group, this is Taine. Because this is proper. Orbits are closed. Another theorem, which will be under our examination next week, but so I don't even properly define the terms now, but you should have this in mind. Every algebraic action of an algebraic group is Taine. Actually, it is constructible. Maybe I will make one remark about it. This is a classical theorem of Chevalier. If you walk over an algebraically closed field, and maybe you know it, actually every map, every morphism for algebraic variety is constructible. This is the theorem of Chevalier. And I will only use it for over C, or maybe I will switch to another algebraically closed field. But this theorem is also correct over any number. So this is more complicated. This follows from Borel-Serre theorem about finiteness of Galois cohomology. If you are familiar with, I will not discuss these things. But you should know it. You should be aware of that. Okay, questions before I move to another subject?
Same but not continuous.
Sorry?
But not continuous. Not continuous, right?
Oh, it is not continuous according to the definition I gave, yes. Okay, we will discuss Zariski topologies later on, we will see, yeah. So, yeah. when I define what constructible action is, I did assume continuity of the action, and those actions are continuous, but not with respect to product topology on G times X, but with respect to Zariski topology on G times X, which is not a product. Yeah, so maybe, again, I was just a little bit slow in the description. So now I want to discuss the Lebesgue category. For short, L space is accountably a generated space and those so accountable. This is Borel. With a measure class. So it is endowed with a measure, but actually I don't care about the measure. I care about all measures which are absolutely continuous to this one thing.
L space means Lebesgue space.
Lebesgue, yes. I will use the shorthand notation that I will do. Yeah, let me keep it. Is that good? Unambiguous enough? Does it mean something funny in Polish? I don't know. And with the measure class of probability or sigma finite measure. So don't just put the measure that I don't know. A too ugly measure. Just take a nice measure. Every sigma finite measure is equivalent to probability measure. I just made this sum up to be able to put in the future sigma finite measures. For example, the Lebesgue measure on R is good. Okay, let me write down. Example. The Lebesgue measure on R. What is the standard notation for Lebesgue measure? M, lambda, mu? It's also an eigenvalue. Too cool. Okay, so this I want to make this into a category. So the morphisms I want to consider are measure class reserving Borel maps defined up to null sets. So actually defined and identified up to null sets. Maybe I will write it down. It's important. So illustrate this. Whenever I have x here and y there, I'm writing down the isomorphism here if actually I can find a full set. And full is something I can define by means of a measure class. A measure class gives me nullity. It gives me the sigma ideal of null sets. And full is something that it's complemented. Is null. This is well defined. And I want to define an actual Borel map into Y or into a conal subset of Y. So this should be a Borel map, and it should be measure class preserving. That is, if you have a null set here, the pre-image of it will be null here. And by such a thing, I will think of a map, an actual map. I will call it a map from X to Y. And if there is another guy, X1, and another map, X to Y, I will consider these two the same. If, say, on the intersection, X intersection X1, they do agree.
Do you mean homomorphism of measured algebras?
So this is, yes, this is the same as homomorphism of measured algebras. I will make this remark. So, equivalent description. If you are a logician, a morphism is a homomorphism of measure algebra. So the category of Lebesgue spaces is dual to the category of measure algebras with homomorphism only. It's not every measure algebra. The measure algebra should be standard. And this is, I took here countable generated. Or if you are an analyst, another dual category, equivalent category, is a category of commutative fundamental algebra. The category, this is the way I would like to think of it most of the time, but probably not in this lecture. The category of commutative, so the full subcategory of fundamental algebra, which consists of commutative ones. Commutative von Neumann. Algebra. Whenever you have a Lebesgue space, X, I can consider L infinity X. Whenever I have a map from X to Y, I can pull back an infinity function from Y to X and get a map from L infinity Y to L infinity X. And this would be a map of these objects, and let me emphasize, when is a commutative fundamental algebra then equivalent or isomorphic to the L infinity function of a Lebesgue space of something which is, I don't know, 0, 1 with a Lebesgue measure, say, or a countable measure on a countable set, or union of such things. This if and only if, which are weak star separable. On L infinity, to L infinity, I have a great dual, L1. A fundamental algebra is actually, W star algebra is the synonymous. Is a C star algebra which has a great dual. Okay? The predual of a commutative algebra, which on the algebra you should think of L infinity of something, the predual is L1. Same thing. And I want this L1 to be separable. I want L infinity to be separable with the weak star topology, and this is the same as this standardless assumption. So the standardless assumption, which may appear, I don't know, well, it's some probability assumption, of course, but it is very natural in this set. So from this point of view, it's very useful. Maybe I will come back to it as a remark in the future. But usually I will denote the space of morphisms x to y. I will denote mainly, I guess, maps x, y. I will put, not now, but I will put maybe a subscript g here if I want them to be commuting with some g action. I need to define a g action still. But when you do ergodic theory, or when you do analysis, many times we want to consider, like in the L-infinity function case, maps from this category to the former one. Maps from Lebesgue spaces into Borel spaces. So let me explain what I mean by this. It's very clear. For a Lebesgue space X, Borel space, typically standard, U, I will use the symbol LXU to denote is a space, as you would guess, of Borel maps defined and identified up to null sets. So it's classes of functions, not actual functions. But you are familiar with many examples of that form, L50, L1. Of course, many times one puts subscript here to say, I know I want some integrability of whatever kind. I want some equivariancy of whatever kind. Okay, so this is the carrier of some further symbols. But just keep in mind that this space maps xy and LXU are of a different kind. And in fact, LXU is a natural structure of a Lebesgue space by itself. Sorry, of a Borel space by itself. I'm not sure about what is the structure of maps xy right now. Okay. So let me remind you something we discussed yesterday. So the category, not the category, the isomorphism classes in the category of Lebesgue spaces are quite double. I mean, you don't have a big variety of them. Every Lebesgue space is Lebesgue isomorphic to either, well, a finite one. In the terminology of von Neumann algebra, this is called 1 sub n, such a thing, if you ever see. This is 1 sub infinity. Well, you may have 0, 1. And union of such. Of course, when I consider those spaces, these are coming with the natural measure classes. The big one here, counting here. Do I forget anything? So you may think that this category is not interesting because you don't have many isomorphism class, but of course categories are not just spaces. These are the arrows too. And the arrows are what is interesting. If we take a group G, for example, I might want to embed it in the group of isomorphism of this Lebesgue space. And this is what ergodic theory is about. Actions of group on Lebesgue spaces. This is the theory of Lebesgue action. So you want G, in order to define such a thing, you want G to be a Lebesgue space itself. So you want G, the group, to have some Borel structure and a measure on it. So the natural candidates should be locally compact groups, which have the Haar measure on them. You want things to be countably generated. So I will take always, considering ergodic theoretical questions, my group will be second countable. So G, locally compact, second countable group. Many times probably I will use the shorthand LCSC group. G goes to the Borel, the Lebesgue isomorphisms of X, and I want this structural of the action to be Lebesgue. Example. First example I should give is the action of G, such group, of course, on G mod H. So we discussed this example. We discussed actually in the past the fact of Miel in this class. So how measure on G? And so this was in the tutorial class. G mod H, a coset space, when H is a closed subgroup of G, always have a canonical Haar measure class. Not necessarily an invariant measure, but there is always a G invariant measure class on it. So this is an example of a Lebesgue space, or a Lebesgue action, this thing. So maybe there are some details to fill out, but this is quite easy, and this is very, very classical, of course. I should say that, and we did discuss this in full, that sometimes you do have invariant measures, sometimes you don't, and this is important distinction. So if you have, I introduced some notation here before. I don't discuss this in full, but of course, if you do act on a finite set, you always preserve the counting measure. Also, if you act on a countable set, if you act on 0 and 1, 0, 1, sometimes you do preserve a probability measure, sometimes only the measure class. Sometimes, if you think of the action of R on itself, you do preserve a measure, but only a sigma finite measure, not any finite measure. So standard notation for this will be 2 for finite measure preserved, to infinity for infinite measure preserved, and 3 if you have an action which does not preserve any measure. Again, I'm not defining this properly, I'm just putting those symbols on the board. If you ever see them, you should think of the relation with ergodic theory. Those symbols appear naturally in the theory of Von-Neumann algebra and the classification of factors. Okay, now I want to discuss something very beautiful. I want to say, well, previously we had this in the last lecture, actually, this is the context of this theorem, we discussed the fact that every Lebesgue space could be made compact. It could be, I mean, essentially, it could be identified with 0. Now Now what about actions? What about the category of the backspace? Can I take this category and represent it into the category of topological spaces? Can I find the representations of all spaces as topological spaces and all maps are topological maps? Of course not. I mean, just take all automorphisms of 0, 1, and you cannot represent these as some homeomorphism group of a topological space in a nice way. When I say, by the way, when I say nice way, I mean I want metrizable spaces. You don't come for me with hyperstonian spaces, please. Not here. What I want to emphasize now is that I can do it, but for countably many morphisms at the time. Okay, so let me start with following observation. So this is observation once we understood how to find a Cantor model to a Lebesgue space for a Lebesgue map. X to y, or a Lebesgue map X to y, we can present, and I hope my terminology is clear, I am not fully making all the definition, we can present as a continuous map of compact metrizable spaces. So I can find a compact metrizable model for X and a compact metrizable model for Y with some measure. So I can find, to be precise, a compact metrizable space with a measure on it, which will be Lebesgue multiplex. Same thing for Y, such that the map here will be represented by a continuous map. And this is very easy, if you remember how we did it. We will just use Cantor sets here. It's very easy if you remember how we did it for one space. So for Y, so here's the proof. For Y, choose this countably generating on bit collection, countably generating collection. Maybe I call it Bn, reserving An for X, Bn, and defined Y to the Cantor set as we did before. Y goes to Bn, Y, okay? And I'll do the same for X, only when doing it for X, I will make sure that the natural map between the two spaces will be continuous by making care that the play images of open sets, or the sub-bases of open sets here, will be open. For X, choose such a collection and enrich it, make sure of including all the p minus 1 Bn. And let me term it as An. AK, take another index. To make it too confusing. Is it clear what I'm saying? And let me mark again X to 0, 1 to the end in a similar fashion. And you have Y, and we mapped Y here. So how the set of indices is not the same. This set is richer. And I'm having, maybe I should think of it as N, union N. Here. I'm describing a proof. I'm not giving all the. I'm explaining. One n is the indices of the generating set of for x, and one for the pre-images pushed from y. And this projection is actually coming from the push, and the pre-image of an open set here will be open here. So the thing is that what is this contouring of a space? If you have 0, 1, the interval 0, 1, well, you have some functions are continuous on it, but if you want the characteristic function of 0, 1 half to be continuous, well, it is not on 0, 1, but I can cut it into two pieces, and on that model of the same space, measurably, or Lebesgue, these two things are just the same. If I didn't happen to have an atom at 1 and at 1/2, these two things, the interval 0, 1 or the third apart interval, are the same space, but the characteristic function here is continuous. And then this is what I'm doing here, countably many times. So again, I leave it for you to fill up the details if this is not clear. Maybe I will define, I will give another approach, slightly more sophisticated to the solving the same problem, slightly more sophisticated, but somehow something that helps sometimes. A compact model for x could be given as well by picking a compact model 2x is the same as, think of it, a choice. Oh, and when I say compact model, I always mean metrizable. In this sense. Of a weak star dense, non-closed sub-algebra of L infinity x. So when you choose a compact model, basically you choose which functions you want to be continuous. You have all functions on x, and you want some function to be continuous and some not. Oh, well, you want all of them to be continuous, but when you take all of them to be continuous, it's like taking the Gelfand spectrum of L infinity x, which is a wild space. It is not metrizable. So I want it to be metrizable, so this is why I want it to be, did I write separable? Ha. Separable. This is an important word which I forgot. I want a separable sub-C star algebra. So it's separable from the norm point of view. So this will make it a C star algebra, and it will have a spectrum which is a compact metrizable space. Metrizable less probability again. But it will be rich enough to fill all the measure because it will be W star dense. W star is the functional of integration with respect to L1 functions. L1 function, if you think of it, not in terms of functions, but in terms of density, L1 functions are just absolutely continuous functions with respect to that given measure that we have. We specify on our space, the Lebesgue space X, we specified a measure class. L1 is just, again, don't think about it as functions now. These are all representatives of that class. When you think about, by the Radon-Nikodym theorem, all representative of that class or weaker classes. So this is the L1, and we want our space to be endowed with a measure saying this. So this is a choice of a compact model, and just if we have the map, let me be brief about it. If we have a map x and y, I can choose such a guy in L infinity y, and choose such a guy with L infinity x, containing the pre-image of this guy. Sorry, other way around. I have L infinity x goes to L infinity y. What is the one? Oh, okay. Figure it out. I want to rush in order to. I thought I would do much more. And now, so this I did only to one function, but now here's the important theorem. Every Lebesgue action has a compact metrizable model. So again, let me give a sketch of proof. First, where G is countable. Maybe it's much easier to understand. Just do that. Take X, take a collection of sets separating the points, but enrich this collection of points to become invariant. Whenever you take Bn, take little gamma of Bn, running over all gammas. This is still countable by the countability of gamma. And this collection, when you give, when we construct this Cantor model, will be, because gamma will act on the space of indices, will be acted upon by gamma. And because gamma will just act on the space of indices, it will respect the topology. And this will be a continuous action. Is this construction clear? Again, I don't want to write details on the board now. So I just write Cantor model. Model rich enough. What about GLCSE in general? The best solution to the problem that I know is to use this kind of point of view. So for GLCSE, there is a name to this question, basically, and there's a name to the theorem. This is called Mackey point realization theorem. Or, well, Mackey point realization is something very close to this. It's not exactly that theorem. But actually, from the point of view of von Neumann algebras, this is very easy to do. And I will only give a very, very brief sketch here. And it is the following. We just want to take in L infinity x such an algebra with all, subalgebra with all these adjectives. Weak star dense, long closed, separable. But G invariant. Okay, so somehow if you just start by taking something and multiply by all G's, it is not good enough, even though that G is second countable. Somehow, if you take just a separable group, this is not good enough. You can't do it. The theorem is not correct. What you need to do is to use L1 of G. Just start with any algebra of your choice, satisfying everything like here, and say A, and take all convolution image with L1G functions. And this will be the algebra that you close it up. This will be the algebra, which is G invariant and rich enough, but still separable, that you need. Okay? So this is really, really very brief. And now a corollary that we get for a Lebesgue action. Almost every stabilizer is closed. Whenever you have a Lebesgue action, you can think of it as a continuous action. So stabilizers in G are closed. Almost every stabilizer are closed. And the orbits are measurable. Okay, this don't need that theorem for that. Orbits are measurable because, well, our group G is sigma compact. There are union of compact sets in the compact model. Countable union of compact sets or countable union of closed sets, so measurable. What else? Okay. Now I want to state, I thought I would prove, but I'm not sure I will have the time, the very important theorem of this integration of measures. So I will first state it as a theorem about continuous function between compact metrizable spaces, but by those kind of tricks, this theorem that I'm about to state, this integration of measures, will be valid for Lebesgue spaces as well. Maybe I'll give a little sketch of what I'm about to do. So this is kind of a Fubini theorem, but for vibration, not for products. So assume you have some sort of a product space, or a space fibered over another. And assume you have a measure here, nu, and on each point y, you have a measure on the fiber, mu y. So you have this family of measures, and it varies nicely, I mean, measurably in some sense, with respect to the structure on y. Then I can integrate function using this collection. If you have function f, I don't know, 0, 1, I can restrict it to the fiber. Essentially, ignore almost everywhere issues, etc. I can just take f of x d mu y x. Just use that measure, but I can do it for every single y. And for every single y, I will get a value here. This result, this is a number. It will give me a function to 0, 1. And I can integrate, this maybe call it f bar, and I can integrate this f bar with respect to d nu. So this is integration over x, this is integration actually over xy, and this is integration over y. And this is a way of integrating functions on the full space x, on total space. So this is a measure. It gives me a measure. A way of integration is a measure. And this measure is denoted, the integral of the mu y with respect to d nu. So this process I described here very briefly is the process of integrations of measures. The theorem that I'm about to write down, and wanted very much to prove, but probably will not, is the converse. Every measure here comes about this way. And again, I will state it now for compact spaces and continuous map. But this is not really an issue by those theorems that we described. A continuous map of compact metrizable spaces. Let mu be a probability measure on x. So this is, you should think about it as the result of this integration. Now here's something which is very easy to do. Define nu on y as it push. Just before I continue, is it clear? push measure. Let me nevertheless say, mu is a functional over here. I want to define a function over here. If you have a continuous function here, just compose C to the function here, mu integrated. This gives me a function on the space of continuous functions here. Or if you wish, if you have a set here, pull back, this is a set here, mu measure it. This gives me a measure of that set. It satisfies all the nice properties of measures, and this gives me a measure on Y. This is a push. So this is why what is less trivial, this is very, very easy operation. What is less trivial is disintegrating mu with respect to this nu. Then there exists a map. Actually, this is a map it goes from Y to the probability measure on X. Y goes to mu Y. It is nu almost everywhere defined. Even if everything is continuous to begin with, everything is as nice as you want, the disintegration process actually is a process that lives in the Borel or the Lebesgue, in fact, world. It will not be continuous, this map. It will not be everywhere defined. Such that, and this is the space of probability measures of X. Mu y actually is supported on X sub y is a fiber over little y. And then what I'm writing here is, of course, for almost every little y. And most importantly, mu is the integral of the mu y d nu y. And this makes sense in that form.
Sorry, but the map is on fibers. This measure is in fibers.
Well, yeah, I mean, of course, the measures on xy is a subset of the measure on x. Yeah, this is, I could have said this is a section of a certain vibration. I kind of try to use less words. So I don't want to give a full proof now, but I want to describe it. It is important term, not too easy for beginners maybe, but certainly for those who knows Riesz integration, Radon-Nikodym derivative. It is not hard to prove. Let me explain this. Basically, what am I doing? I think I did describe. Well, we did describe in full how to push measures. This is very easy to do, and I can actually push N1 functions. I think about those as measures, and I push them. Actually, maybe I should stop. If I have an N1 function, stop and say the following. If I have an N1 function here, I can think about it as a measure and push it down and get a measure here, which is well, what do I mean? I have mu here, and if you have an L1 function f, I can have the measure f times mu here. A measure which is absolutely continuous with respect to mu. I can push that measure here, and I will have some measure which is easy to see to be absolutely continuous with respect to nu. So by Radon-Nikodym derivative, it is some f bar times nu. So f bar is the push of f. Let's think about it this way. Okay? From where I am standing, knowing the theorem, actually I know what f bar means. F bar is the integration over fibers, as I described here. But we don't know this one yet. This will come up as a bonus. But we do have, we can define, even without introducing the fiber-wise measures, we can define that push, f bar. Again, by the Radon-Nikodym derivative. bar will be an L1 function. Even if you have started with a continuous function f, the result f bar will be only L1 function, so it will not be defined everywhere. So, but it will be defined almost everywhere. So now, don't do it for all L1 functions on X. Take just a dense collection in the continuous function on X as your test functions, and do it to them. Push them down. Each of them will define a full set in Y. Take the intersection of these. This will be the almost everywhere that appears here. Take countably many test functions in X, push them down, and think of these L1 functions. And now, I want to claim that each point Y define for me a functional on these countably many functions. Just evaluation at the point. Right? If I have a function, I push it down, and on the domain that they are all defined, I can evaluate the function. For a given Y, I'm getting an evaluation at the point. So this is a functional on this dense subspace of functions here. It is a well-defined functional. But this functional is easy to see. Now I have to write down things, so I'm not doing it precisely, but it is easy to see that it is of norm 1. So extends to the full space. So it doesn't really matter what kind of dense subset I was using it to begin with. It extends. So it gives me a function on the full space of functions Cx. And this functional on Cx associated with the evaluation at Y will be the guy mu Y that I'm seeking. Okay, so for those of you who are happy with oral explanation, I hope you are happy. If you find yourself that this is hard to follow, just look it up in the literature. But this is an important piece.
How much is compactness that the price of build is important here?
Also, again, I want to end this class, so I don't want to formulate again another theorem. But it is not important at all. I can replace x and y by Lebesgue spaces, just picking the models. And maybe I should say, my last remark is, typically, when I will use it maybe this in the future, x will be a tame action of G, and y will be the space of orbits. And the result here will be that if you have a tame action, every measure on it is actually disintegrate nicely to measure on the space of orbits. Okay? So I need tameness in order to make this a nice space, so I can apply this theorem. But this is, yeah. Basically, this process of disintegrating things into G orbits is called ergodic decomposition. But in the presence of a tame action, this is something very, very nice and explicit. So this is the end of my talk.